Buenas tardes, bienvenidos, bienvenidas. Bueno, como saben, tenemos el honor de recibir hoy en nuestras instalaciones la visita del profesor Srdjan Nesic, quien es un experto en el campo de la corrosión. Sé perfectamente que todos asistimos aquí a escucharlo a él, pero voy a tomar 2 o 3 minutos de su tiempo para hacer una presentación adecuada de su currículum, si así lo tienen bien. También bienvenidos a la gente que nos sigue en el canal de YouTube de nuestra facultad. Entonces, el doctor Nesic es profesor distinguido de la Universidad de Ohio y es Ross Professor en Ingeniería Química en el Departamento de Ingeniería Química y Biomolecular en Athens, Ohio, Estados Unidos. Desde 2002 también se desempeña como director del Instituto de Corrosión y la Tecnología de Flujo Multifásico en la misma universidad. El profesor Nesic ha publicado ampliamente en el campo de la corrosión, incluyendo 18 trabajos clave en handbooks que hoy nos sirven para todos los corrosionistas como guía, específicamente en el Corrosion Handbook y el Shears Corrosion, abordando la corrosión y erosión con aplicaciones en la industria del petróleo y del gas, sobre todo. Es autor de más de 160 artículos revisados por pares, 260 comunicaciones en conferencias y más de 100 informes científicos en el campo de la corrosión. Sus publicaciones han recibido más de 20,000 citas. Es fellow de la NACE, AMPP, y se desempeña como editor asociado en la revista Corrosion and Corrosion Science. El profesor ha recibido numerosos premios y reconocimientos, como el premio Willis Rodney Whitney, otorgado por la NACE en 2018, en reconocimiento a su importante contribución a la ciencia de la corrosión. El premio al mejor artículo en la revista Corrosion, tanto en 2010 como en 2015. El premio Huglich, otorgado en reconocimiento a la destacada efectividad en la educación en corrosión postsecundaria en NACE. Esto fue en 2007. Y también el premio Ben Gogh al mejor artículo en la revista British Corrosion Journal en 1998. Sus estudiantes de posgrado han ganado el premio Campbell en 2 ocasiones, en 2009 y 2015, al manuscrito más destacado publicado en la revista Corrosion, presentado por autores jóvenes. El Instituto de la Corrosión y Tecnología de Flujo Multifásico, donde el profesor Nesic ha sido director durante mucho tiempo, recibió el premio de la organización NACE para 2020 como una de las instituciones clave en el estudio de la corrosión. Ha presidido numerosas sesiones en conferencias internacionales y ha dictado numerosas conferencias. Ok, quizá aquí una parte muy relevante de las actividades del profesor son las asesorías a la industria, ¿no? Entonces, ha asesorado a la industria en múltiples campos y en múltiples ocasiones, en temas como corrosión, erosión, flujo, transferencia de calor y transferencia de masa. Algunos de estos trabajos se relacionan sobre todo con el diseño de las plataformas marinas con el diseño de campos, de gas en Kazajistán y en Australia Occidental. También con plataformas marinas en el Mar del Norte y en las costas de Canadá. Y un dato, pues también muy interesante, es que ha trabajado en varios casos legales como testigo. Estos casos legales son tan importantes como los siguientes, ¿no? Fue testigo experto en el caso de la demanda que el estado de Alaska puso a British Petroleum relacionado con el incidente de la bahía de Prudhoe. También fue testigo experto en el caso del DOJ contra la British Petroleum, también por un accidente de derrame de petróleo. Y también fue testigo en el caso de Alcoa, que puso Alcoa contra la KAPL. Bueno, sin más, le cedo la palabra al profesor. Professor Nesic, the floor is yours, please.
Hello, everyone. I apologize, my Spanish is not good. So I will speak in English, so I hope you will understand me. I will speak slowly, and I hope I don't have too strong an accent. I think I understood everything you said. I think it's correct. Very pleased to be here. A pleasure to be in Mexico City, and particularly my pleasure to talk at this university. I do know a lot about this university from the past. I had 4 or 5 students, graduate students, masters and PhD from these universities that came to study with me. And of course, I met Professor Montoya, and we are talking about some very interesting things and possible collaborations. The reason I'm here, and I'm here since January 2nd in Mexico City, is because I'm on a sabbatical. You know, that's like a period when I can do and go places I like to go, and I chose to come to UNAM. It's one of the key places to, for a few reasons, to establish a collaboration stronger. I did collaborate previously a little bit with Professor Nesic, but also with some younger folk, and also to see the students, hear what they're doing, and hopefully motivate them to also come to Ohio and establish the collaboration, and maybe even continue their education there at some point. So all of those are the motivations for me coming here. So, so far it's been a wonderful experience, and I hope this lecture will inform you a little bit about what I do. It looks like a pretty complicated story, and it is. It is about anodic dissolution of iron, so corrosion of iron. It actually means to address steel, corrosion of steel. And that is the area that's very close to my heart. So I work with corrosion of steel, whereas, for example, Rodrigo works mostly with aluminum alloys and some other passive metals. We focus on steels, and I will show you a little bit more about our activities in Ohio. So the topic today involves 2 quite difficult techniques that have been used in this particular study. EIS, electrochemical impedance spectroscopy, which is probably one of the most difficult to interpret electrochemical techniques. I don't claim to understand it very well, but I try, and I will share what I do understand about it today. There may be experts in the room here who will help me with something, and I will try to keep it fairly high level, superficial, because I know there's a lot of people here who don't know much about electrochemical impedance spectroscopy, and that may be like just not really something they care about. So hopefully, you know, you also see something interesting there. And the second part is something I know even less about. This is this TOF SIMS, which is a fantastic surface analytical technique that has been used, and I will talk about it. Now, I was part of this bigger project. You can see there's many co-authors there. The first few are all my graduate students and postdocs from Ohio University. The other 3 individuals are from Paris, from 2 different schools in Paris, France. The first 2 are from Paris Tech. They're the people who have this TOF SIMS, and the last person, Alan, is from Sorbonne in Paris. So we have very tight collaboration. Actually, these 2 students have spent 3 years in Paris, so we shared the students, and they did some work over there, some work at Ohio, and then we finally put this whole story together. This is now being considered for publication. It is being reviewed for the Corrosion Journal. So this is pretty fresh, you know, not even published just yet, about to be published any day, I hope. So, you know, I will try to, as I said, talk about both techniques in a way that all of us can understand each other. So if you have questions, please do. I will try my best to answer them. So this is the structure of my talk. I will spend the first 10 minutes or so talking, you know, it's Athens, but not Athens, Greece, it's Athens, Ohio. There's 12 different Athenses in US. And they're all places of academic learning, of course, named after Athens, Greece. Athens, Ohio is nothing like Mexico City. Actually, I think all of Athens could probably fit into the campus here. That's how small it is. I'll talk then a little bit about why we did this study, and finally get into the details. So, let us start. This is supposed to work. This is Athens. I will show you, this is a map of Athens. As I said, I think UNAM campus is larger than this area that you see here. If I run this movie, you will get a bit of a picture, if it works, where it is. So we're zooming out here. So Athens is in the state of Ohio. You will see some cities you maybe heard about. Columbus is the capital up here. Cincinnati is another big city. Cleveland up there. And then you can see Ohio is kind of in the northeast of the country. Right there where that arrow is. And of course, we are now all the way down here in Mexico. So it's pretty far away, but not so far away in the end. And a little bit about Athens itself. Hopefully this little video will show. It is a small college town, nothing except the university. So if you can imagine, it's like UNAM with only the woods around it. There's nothing else. That is what it looks like. So some pictures, hopefully you get a bit of a feel. It's a very nice, quiet, crime-free, problem-free place where we have very green. We have lots of students there. Well, not lots like here, lots. We have 25,000. You have 373,000 here, so it's a bit different. But it's a relatively big university. It's the 10th oldest university in the United States. 10th oldest public university in the United States from established in 1804. So fairly old by American standards, and a comprehensive university that has all different types of colleges there. And in engineering, we have pretty much every type of engineering. I belong to chemical engineering. These two guys are my students. So the institute where I work, and which I'm going to show you, belongs to the chemical engineering department, which belongs to engineering, which belongs to the university. Of course, we have all the other branches of engineering there. We don't have materials. It is not part of engineering. It's actually not part of any of the colleges. So materials are kind of part of chemical engineering, but not really. We do not offer a materials degree, funny enough. But anyways, that's as far as the university. The ICMT, Institute for Corrosion and Multiphase Technology, has been around for about 30 years. I've been there for 21 of those, last 21 as the director. And it is meant to be one of the biggest and most important facilities related originally to oil and gas production and transportation. So we're talking this massive industry with massive infrastructure, and we focus mostly on pipelines, which are made from steel, regular steel, mild steel, carbon steel. And we focused, again, almost entirely on internal corrosion, not the corrosion from the outside, which you may have seen before, that, pipes rust. That is actually not a big problem. The problem is from within, from the inside, when oil and water almost always come out and create corrosion problems that are hard to see, impossible almost to predict, and when the problem appears, it's kind of too late. The infrastructure that needs to be built to study such types of corrosion is big and complex, and that's why we have this big laboratory there and work on it actively. We are different from most academics, even in the US and probably here, in that we are funded about 98% from the industry directly. So all our funding that funds students, postdocs, research comes directly from the industry. Most of that oil and gas industry, but also chemical industry, steel producing companies, etc. Of course, our business is like yours. We produce young people with good education. They go on and try to make the change in the world and make an impact. But we do that in this way, that we fund our research, which they work on directly from the industry. Pretty big group by corrosion standards, about 40 of us, half of them students, masters and PhD, the other half academics. And I've been the director for way too long, a few more years probably, and then there's some young wolves in the background there. They're going to take over. So it's a nice big organization. We have full-blown faculty, tenured faculty. We have a number of what's called research faculty. They don't teach all the time. They're focused entirely on research, and they're funded by the industrial funds, not by the university. And then we have these external guys who are usually some of the best people from the industry who are interested in academia, and they actively participate in our research. Many of them retired and still want to be active, that come and help us. So a pretty big group, and then we support the students also with the help of postdocs and other engineers shown here. And we have a rather diverse group, about 20 plus graduate students, mostly PhD from various parts of the world. No Mexicans at the moment. As I said, I had 4 or 5 in the past. They all graduated and moved on to various places. And they work in various projects. Most of our projects are so-called joint industry projects, JIPs, and they are funded by different groupings of companies as shown here. I'm not going to get into that in any big detail, and we are very proud of our students. This is most of them that have graduated in the past 20 years, and they ended up, most of them, again, working directly for the industry. Only about 10% ended up going back to academia to teach in various universities around the world, but most of them, as I said, ended up working for the industry, and often for the industry that was involved with their studies. So a few pictures of the lab. It's a big lab, the size of a football field, just to give you some kind of a measure. A lot of large equipment, because in these pipes we have to create multi-phase flow. We have to move oil and gas and water and sometimes even sand, and then we have to study internal corrosion, what happens on the inside. So, it's difficult to make it happen in a glass beaker. You have to go big. Pressures are high, sometimes even above 100 bars. Temperatures can go up to a few hundred degrees. So it is pretty demanding and heavy-duty experimentation. Some of our systems, flow systems, actually incline and go from horizontal all the way up to vertical. We have autoclaves and a lot of different stuff. It's all required because you don't need to do everything in a big piece of equipment. Some things can be done smaller, but you have to kind of tailor it. We build all our equipment, just like most academics do. We don't buy these things. We design them and then build them around the country and put it all together. These are some of the big 20-liter autoclaves that we put together. Pretty high, you see 140 bars and 80 degrees Celsius. Of course, we have this glass type of equipment as well, which is extremely useful. I don't mean to say that's not important, it is, but not everything can be done there. From the analytical side, the usual things, profilometry, this is optical profilometry, scanning electron microscopy, EDX, we have XRD, we even have atomic force microscopy. I don't know, you may have it here as well, very interesting for surface studies. But it's not really a piece of equipment when you buy it, it's a project. You have to have someone spend 2-3 years learn how to use it properly, and then maybe you get some good results. Very difficult, but very powerful, of course. So that's kind of a brief overview of where I come from, who we are and what we do. We get funded mostly by big companies, oil and gas companies, chemical companies, and it works. It has worked very well for the past 20 years, and I hope it's going to work really well going into the future. It's not like we don't like money from the government. It's actually very sweet, but as here probably is the case, it's difficult to get, very competitive, and I feel often very unfair who gets it. So we are used to, and we work very effectively with the industry. And being an engineer, I like working directly with the people who actually want to use what we do, rather than with some bureaucrats in the governmental structures who don't really care what the results we produce are. They're the intermediates. So I really enjoy this model, and I really recommend it to some of my younger colleagues. All right, that's it. Let's talk a little bit about the scientific topic of the day. It is iron dissolution. It's an oxidation reaction where iron dissolves. Not all of you are corrosion people, but you get it. Of course, you heard of it. So iron, of course, something has to come and take those 2 electrons, an acid or oxygen or some electron-liking substance. Usually it's oxygen or acidity. But generally, I'm not going to focus on that other part. There's been plenty of work done there. We're going to focus on this iron reaction. So look, what's to focus on? It's simple. Iron gives 2 electrons and it's over, right? It's done. No, that's not how it happens, actually. It may look like, why doesn't it happen that way? Well, first, if you look at it, you have 1 atom of iron giving away 2 electrons. That never happens at the same time. It must be 1 and then the second one. So there's going to be at least 2 steps, if not more. So that immediately tells you this cannot be right. Actually, it turns out, if you want to model this and somehow calculate it, or even if you do experiments, pH has a big effect. It's like, what? pH? There's no pH. There's no hydrogen ions. There's no hydroxide ions. What's pH got to do with it? but it has a major effect of how this reaction happens, slowly or fast. So that's another indicator, cannot be happening this way, it's got to be something else. This must be the overall reaction, but there must be a lot of complexity, a lot of fine details that we don't see when we write it this way. And by the way, this is what everybody writes in every book, almost. It is true, this is not wrong, it's just not the whole story. So, oops, sorry, I don't know what I pressed. So, again, sorry for those of you who are not into electrochemistry, but the way we study this, we essentially provide different electrical potentials to electrodes, and then we watch the electrical current. Sounds like we're electrical engineers, but no, that's not what it is. This is electrochemistry. What happens here, when you change the electrical potential, essentially you provide electrons, more electrons or less electrons, and then you see what is the response. How many of those electrons are taken and how fast? Which is this current thing. So when I show these current voltage curves, they actually tell you about what is going on, what is this reaction doing, how many electrons is it taking, how fast, in which way, what affects that. So electrochemistry is an extremely powerful tool in studying any electrochemical reaction, including this one, which is part of corrosion, right? And then there's different behaviors. Down here we have what's called active dissolution. That's where iron dissolves in a very simple way, and then, and that's indicated by this line. There's a direct relationship there, which is purely theoretically described with the Butler-Volmer equation, but then it does some weird things. It actually goes backwards, and then it goes forwards again, and goes backwards again, so it's like, whoa, this is something more, and those other behaviors are called pre-passivation, and then up there, passivation. That passivation is a bit like stainless steel, or aluminum that they work on here. So I'm not focused on that. My focus is going to be mostly on this active dissolution, because that's where this reaction matters. That's where, in acidic solution, that's where you are. You're down here in the active dissolution region. In very alkaline solutions, you could go all the way up here, but that's not what my story is about. It's about acids and acidic solutions. So, it's not like we started working on this for the first time ever. People have been doing this for 50 years, maybe even 80 years back. Steel and iron was an important metal forever, actually, since our civilization, right? So its corrosion and how it happens has been always of interest. And many years ago, I think in the 50s, there's a German guy called Heusler. He proposed this is actually how it happens. And I don't know if you can read that from back there, but there's like 3 steps. And if you add these 3 steps together, it comes back with that simple reaction I showed you at the beginning. But this is what it happens. And you see here now some hydroxide species show up, something that wasn't obvious, that sort of cancel each other out when you add it together, but they're there. And they matter because, for example, in his story, there's actually 2 series of reactions, and this red species, this ferrous hydroxide adsorbed, that's the key. That's where that pH thing comes in. And his whole mechanism, pretty complicated, hangs on this, that there is this pathway where first you make this species, and that species is catalytic, and then it helps iron dissolve. So, very complicated story. And if you're like me, when you first read this, you say, how does he know this? How did he come up with that? I mean, I can write another 20 different schemes like this, and all of them may look right. So how does he know that this one is correct? Well, okay, one clue is it's got to be a pH-dependent reaction. So it's got to have some hydroxide or H pluses. So there's his first, but then, okay, yeah, but then I can write another 30 different schemes like this that all have hydroxide in them. So which one, how does he know that this one is correct? All right, now the guy did a thorough job, and he compared with some experiments and, tried to convince himself, and others followed that yes, this is probably the correct mechanism, even if they could never detect any of these species. They didn't know, they just kind of measured the answer, and it seems to fit. The overall answer seems to agree. Then comes another famous electrochemist, maybe 5-10 years later, Bockris, who you may have heard of, probably one of the fathers of modern electrochemistry, and he says, no, it's much simpler. It's actually like this. Only 3 steps, and in those 3 steps, okay, the same kind of bad guy shows up, this hydroxide, but it's a different scheme. There's no catalysis or whatever, it's much simpler. And of course, they show experiments and say, see, it fits with our experiments. But again, they have no direct evidence. Actually, they have no evidence that it is this hydroxide at all. Maybe it's something else. How do they know that? Fast forward many years forward, in the 80s, there's a French famous electrochemist called Kedam, and his group, they say, well, you know, actually both of those guys are correct. It could be both mechanisms happen in parallel, and they kind of take over from each other in one range. The one mechanism, and then it kind of switches to a second one, and actually he proposed 3 parallel paths, and call it a multipath, and it looks like this. And you can't even read those letters, and that's good. You don't need to. I mean, there's nothing there that you can absorb in a lecture like this. But just absorb this, like he says, it happens in 3 parallel. The first one is more like Heusler, the mechanism I started with. The second one is more, Bockris. The second one is more like Heusler, and this one here. And the third one is a completely different. And he proposed some other complicated species like this adsorbed hydroxide on iron, which he gave a separate name, etc. So even more complex. And then of course you go, well, how does he know that? You know, this is even, I know he kind of united all 3 together, and you know, why is he right? And he backed it up. If I fast forward here, he did the whole model thing, and he said, well, one of those reactions behaves like that, the second one like that, the third one like that, and when you add them together, you get this curve, and you know what, it looks very similar to what reality looks like, what they measure. So the reason that all these reactions go forward and then backward is because they all happen on the same surface. And the surface is only so big, so if one reaction takes 80% of the surface area, the other 2 can only share 20. So these coverages change as the reactions happen, so that's why one kind of dominates and then loses territory, and another one expands on the surface, and then he loses territory, and the third one expands. Pretty smart, right? Good story, and you know, maybe he's right. So we said, okay, let's start with that. That sounds flexible enough. Let's see if we can work with that complicated story. And our business is to look at the effects of 2 things, chlorides and CO2. So the question is chlorides and CO2 in the story. So do they make a difference? And if you look at this scheme that I just showed you, this one here, the most complicated, there's no chlorides there, and there's no CO2 in there. So your answer should be no. Chlorides or CO2 should make no difference, only hydroxide, only pH. Well, that's not how it happens. Actually, both chlorides and CO2 have an effect on this reaction. And they'll go like, wow, come on. I mean, it's complicated enough. What needs to happen there? So we went forward and looked at the literature, and you know, I messed around with that many years ago and I got it wrong. And then other people's messed around with it, and they had some stories. It happens, it doesn't happen. Pre-passivation, passivation. I don't want to bore you. Again, this is not a venue. I'm going to skip. This is one of my research students did these polarization sweeps, and these are for 3 different amounts of CO2. Red is no CO2, 1 bar CO2, and 5 bar CO2. That's a lot of CO2. And sure enough, there was some response. So yes, this curve that represents iron dissolution responds to CO2. It also responds to chlorides, I will show you. So it's like, wow, what is going on there? So I'm going to skip this and just say where we went. We said, all right, we're going to try to use the best possible electrochemical technique that looks at the mechanisms, which is this electrochemical impedance spectroscopy, which I'm going to bombard you with a few slides in a second. And then I was very lucky to be able to use these TOF sims as a completely different technique to try to kind of verify some of the results. And you will see that's the subject of today's talk. And I wanted to see, you know, does CO2 really matter and how, and do chlorides really matter and how? Chlorides have been dealt before. A lot of people said chlorides do matter. They even had some hypotheses how, but they weren't sure. So let me start with EIS first. Again, crash course. This is one of the most complicated electrochemical techniques, not to do, but to interpret. It's easy to do. You apply an electrical signal, you know, like an AC, like the stuff from the wall, that goes up and down, and then you put that voltage in and you see what the current does. So you end up producing some kind of response curves, which can be shown like that. So here is your input voltage down here, so you vary the voltage in various frequencies, and then you watch what happens to the current. Of course, it also goes up and down, but the frequency can be different, and also the amplitude, etc. And all kinds of complicated things can be figured out by doing this. So it's a very rich, data-rich technique, because you can do this at various potentials, with various amplitudes, with different frequencies. So like a lot of information is generated, and then the question is, well, what does it all mean? And that's the million-dollar question when you use EIS. How do you interpret that? And one of the common ways to do it is to draw something like looks like a Nyquist plot. It'd take me probably an hour to try to explain the details, but essentially you, in this type of representation, you produce these semicircles. And each of the semicircle is a characteristic for one of the underlying processes that are happening. So it could be an electrochemical process, like dissolution. It could be charging of the so-called electrical double layer. That will be another loop. It will be a diffusion of species. That will be another semicircle. And since all of these processes have different kinetics, some are very fast, like charging of a double layer of the surface happens within microseconds, very fast, whereas diffusion of species takes seconds to happen. So when you apply different frequencies, different things will respond, different parts of the overall process will respond to different frequencies, because the fast one will respond when you go megahertz. Diffusion will respond when you go down to a hertz level. That's when it's going to start dancing with your voltage, right? So it sounds like magic, right? You have this technique, you apply this whole spectrum of different potential variations, and you are able to see what everything's doing. Well, that's theoretically like that. The reality, much more complicated than that, and you'll see that in a second. So, this student of mine, she now has graduated and gone, a PhD student, did all kinds of experiments in chloride solutions, in sulfate solutions, with CO2, without CO2. Took her only 4 years to understand what she's trying to do, and then another 2 years to actually do it, and got some pretty good results. So, I'm going to really go quickly over her main results. So this is the kinetics diagrams that I showed before, one in sulfate solution, one in chloride. Yes, so chlorides matter. No matter what you do, you change the chlorides versus the sulfate, things change. It shouldn't be. Sulfate is a supporting electrolyte. Sulfate is supposed to be inert. And so is chloride. It's not part of the reaction, but actually it does change the rate. So, she wanted to see how and why, so she did, if I kind of indicate this, she polarized both solutions, at one potential here and then another potential, and compared. Say, well, I want to see, but then she used this electrochemical impedance. She jiggled the potential and tried to see what happens with the current. So, here's the one. At some potential, you can see like there's like 3 semicircles. There's one here, that's actually charging of the electrical double layer, very fast. There's another one here, and another one. So there's like at least 3 different processes that happen. Frequencies go from very high frequencies in the kilohertz, even megahertz area, to 20 hertz, to 0.1 hertz, to 0.001 hertz. Some processes that happen over 0.01 hertz is like take 100 seconds to change something, or 1,000 seconds. So really slow process. And you can all recognize them here. Once you do this for a few years, you tend to know what's what. This is charged double layer, this is probably some electrochemical process or adsorption, and this is probably something else, even slower. But anyways, she said, okay, can I map these semicircles on this scheme that Quédam, this French scientist, proposed? And yes, you can. If you believe him, this semicircle is that, and this semicircle is something else. Again, too much for you to absorb in this talk. So what my student did, so I'm going to do it in chlorides. And she got a slightly bigger semicircle, which is no big deal, believe it or not. That's a detail. You can make the circles the same size. What matters is the number of these loops, these semicircles. So there's this one here and there's that one there. And this one happens at 20 hertz, this at 40 hertz. That must be the same thing. Frequency is the same, the shape is the same, that's got to be the same process. So no difference in this process when it comes to chlorides versus sulfate. Then there's this loop down here underneath the axis. This is almost at 1 hertz and this was almost at 1 hertz. That must be the same process, so no difference between the two solutions. And then there's this one, and all of them seem to be the same. Whatever was happening in sulfate solutions, what's happening in chloride solutions. You go like, oh, okay, so chlorides make no difference, right? Well, not at this potential. Then she increased the potential to an even higher level, a little more positive, and the same thing happened. No big difference. And which is really also indicated because these two curves are kind of close to each other, they really separate out up here. So when she raised the potential even higher, she saw two loops in sulfate solutions, but you can see already, even if you're not expert, that this shape of this curve is kind of similar, but there's like one more jiggle. There's this loop here, which is this one there, and then there's like, oh, one more, and that one didn't show up there. It's like, one more process is happening now in chloride solutions that wasn't happening in sulfate solutions. And then she did an even higher potential, and long story short, again, she saw one extra curl. So there's this process here in sulfate, and here it is in chloride, and then there's one more curl that goes down that happens that doesn't exist. Of course. What does this prove? Nothing, except there's something else going on in chloride solutions that did not happen in sulfate solution. You analyze and talk about it, and I'm going to skip all the stories and get one more potential. And she said, you know what? There has to be, I'm going to go fast, there has to be a fourth pathway. The first three are with hydroxide, and this one is with chloride. So chlorides adsorb on the surface and displace hydroxide, and they're now becoming important at certain conditions. So that's an even more complicated scheme now that has 4 pathways for iron dissolution. Of course, any of these pathways, you add it together, you get that first reaction that I said is too simple and not really true. So this iron dissolution happens according to this story in 4 different pathways, parallel, and each of them has its own kinetics and its own importance, and some depends on chloride concentration, so more salt, less salt, other depends on pH, more hydroxide, less, third depends on, oh my God, complicated. And of course, you remember my skepticism from the beginning. How do we even know that any of these species on this scheme are correct? We just made that up. It seems to fit, but there can be another clever guy or girl and says, well, I'm going to write a different one, and that may fit as well. So which one is correct? This one or that one? And maybe we're totally off. So I'm going to skip CO2. CO2 is because I don't want to bore. I'm going to skip that whole part of the story in order to give more time for questions. So she concluded, my student, Megard, that chlorides do make a difference, and they form a 4th pathway in the dissolution of iron. First 3 are correct, that get up, and then there's a 4th one. So of course, then the question is, how do you know? There has to be some proof that chlorides are actually at the metal surface when it corrodes, that they're actually involved there, that they're part of that surface the same way as hydroxide is. She speculated that that is the case. Other people speculated before, but there was no direct evidence. So, when I saw this opportunity with Professor Marcus and his group in Paris to actually bombard this surface and try to see what species are actually on the surface, is there really chloride there? That was a fantastic opportunity. So I learned about this technique only a couple years ago, the details. So for those of you who don't know what it is, it's kind of fairly simple. They have this beam, ionic beam, that they shoot, very high energy. Essentially, when it hits the surface, it explodes the surface. The first nanometer or so, maybe less, just the first layer of atoms. It's nicely tuned. It's makes it all kind of fly in all possible directions. And then they have a column, tall column, vertical column, and those ions fly up, but of course against gravity. And they slow down. So the heavy ones take longer to get there, and the light ones are faster. And they have detectors up there, and they keep registering when these ions that have been exploded at the surface, how long it takes for them to get there. That's what is tough, time of flight, how long it takes for them to fly up to that detector. And then they do some other fancy spectroscopy, but that's the kind of the essence. So by knowing how long after hitting the surface they pick up the signal, they can say this must be this molecular weight of the compound or the molecule. or the ion. And then they go and say, well, what could it be? And then they have this complicated analysis and they figure out, oh, it is this compound actually that we detected. So by detecting all the different compounds that take different times that reach the detectors, they can figure out the surface must have had such and such things on before we hit it with this beam. Phenomenal, right? And then they have this sputtering gun, which is not as high intensity, and they kind of remove a layer and then do it again. And remove another layer and do it again. So they get a depth profile of these, what's on the surface and what's a little underneath the surface and underneath that and underneath that. And they can go nanometers deep. Well, you can say nanometers is not exactly deep, but we're talking surface stuff. It is pretty deep. So then they produce really beautiful pictures, either two-dimensional. This is like a picture looking from the top here. They can get these colors and say what is the distribution of various compounds. Or they can create a three-dimensional image of a particular compound. Is it only the surface? Is it a little bit underneath the surface? What happens after a certain amount of time? I don't want to bore you. It's a complicated techniques. And they make these wonderful graphs. This is depth here, how deep it is, and after sputtering, and then they see, in this particular case, there's like chloride and FeO2 minus and Fe2 minus and FeOCl minus. They detect all these different compounds, and they can create either profiles like this, or they can create 3D images like that. And these two, I think we're going to focus on these guys because they're easier, more intuitive. You can see here that initially, this thing detected there's iron, because they have this ion Fe2 minus that flew up and they caught it. And there is this thing called FeO2 minus. So there's a little bit of oxide there before even the experiment started. And that's called contamination. That's called the oxide, that probably comes because you have oxygen in the air. And even if they do experiments trying to eliminate oxygen, there's always a little oxide on there before they start. And they pick it up. And you can see it's there on the surface, and below it is actually pure iron. But above it is like oxide. How thick is this? Well, if you look at this signal here, if you take that, it's 2 nanometers. Oh, so it's only a couple molecular layers of iron oxide that are there before they even start the experiment. Then they put it in water, then this thing corrodes, and they take it out, and without exposing it to the air, they take it into this instrument and do the analysis again. By the way, there was almost no chloride there, and this is what the picture looks. So some maybe traces of chloride, a layer of oxide, a few nanometers, and then the rest was iron. That was the big, before you start the experiment. And then they do an experiment, and if you look at iron, of course it corrodes. So you can see that, you get these kind of roughening of the surface. Iron surface becomes very rough. Again, remember the whole thing is 2 nanometers. So it's not really as bad as look here, but it gets very rough. So, surface is corroding. They can tell that. You can also tell from these plateaus up here. It doesn't matter. And then they say, well, let's look at this hydroxide. There has to be now a serious amount of hydroxide on the surface, iron hydroxide, if that theory is correct, the Kedam theory, the theory my students use. There has to be a compound that has hydroxide in it there. And sure enough, there was no hydroxide more or less to start with. And then after 3 minutes, it showed up, and then 10 minutes even more, and then after 1 hour, there was this hydroxide. Wherever there was iron, there was hydroxide. So here's your independent proof. It is a surface species. This iron hydroxide is a true surface species detected by Toph Sims. It's not just an imagination of those electrochemists that had to come up with something. It's true. It is there. All right, cool. What about putting it all together? And here you can see here, so initially the surface is there. There is no hydroxide, a bit of oxide there to start with. And after a while, there's hydroxide develops and basically is there all the time. Here's your black is iron, purple is hydroxide. So you have essentially the layer of hydroxide always during corrosion on the top of iron. So if this iron is going to dissolve into the solution, it first has to become hydroxide and then it has to go into the solution. It can't jump out, it just cannot send electrons out and go out in the solution. It does have an intermediate species, in this case hydroxide. So Heusler in 1954 was right. And so was Bockris in 64, and everybody else that followed. Not a new story, but here is a direct proof. Yes, these hydroxides are an integral part of a corroding surface. So they were right. So Kedam's Story and Bockris and Heusler, correct, and they have been, verified by Tov Sims. They've been verified other ways, but this is quite a new way to kind of show that yes, they're right. So what about chlorides? They're supposed to be there as well, right? Because my student said, and followed some others who said, yeah, it kind of plays the same role as hydroxide. It absorbs on the surface and makes these compounds, and iron dissolves by first becoming a chloride, some chloride compound, and then it dissolves into solution. It doesn't go straight into solution. So here is the blue is this profile of this FeOCl minus, which is some sort of an indication of a chloride compound on the surface. And if you look at it, basically nothing to start with, and then it starts developing, and you have these kind of localized chloride contents as you go deep. So chloride doesn't kind of cover the whole surface, but it forms like islands. So if you want like pits, but you have to remember this is only a nanometer across, so whether you want to call it a pit. And in the end, after 1 hour, lots of these chlorides as part of the surface, and I think she puts it all together to see here, combines it with hydroxide. So essentially you have hydroxide and chloride simultaneously developing, but sort of independently. Where you have hydroxide, you don't have chloride, and when you have chloride, you don't have hydroxide, but both of them cover different. Well, it depends on the pH. If the pH is low, you don't have much hydroxide, so that pathway is hard. And vice versa, if the pH is high, then you have a lot of hydroxide and that pathway is easy. Same with chlorides. If you have very little chloride, that may be irrelevant, but if you're like in salt waters, 3%, that's a lot. Then, if you have 20%, then it's like absolutely dominating. The surface is totally covered with chloride, not hydroxide. So it makes a huge difference, and the kinetics of iron dissolution will respond accordingly. So we have, in this part of the study, proven explicitly that this alternative pathway for iron dissolution, the chloride pathway, is actually true. Maybe we don't have every detail, right? We don't know exactly which chloride complex it is. Is it Fe something something chloride something something? We don't know that because we don't have an analytical technique to tell us exactly what the compound is on the surface, but we know that it has to contain chloride, and it's a compound because we got it by bombing the surface with ions and exploding it and detecting it. All right, so here are the nice images which show, before immersion you just have iron and a bit of oxide. After a while you have iron and a bit of chloride and hydroxide, and then in the end you have a really big mixture of iron, chloride and hydroxide on the surface of metal. All right, I decided to skip this part with CO2 because it would just kind of show you more of the same, and I would like to end here, Rodrigo, and rather than talk for another half an hour, open the floor to questions and see if you want me to elaborate on anything I said. Thank you.
Thank you very much. So we have time for questions.
Don't be shy. You're shy, I'm going to continue talking about CO2, and you don't want that. So better ask me questions.
Okay, meanwhile, I can ask you something.
Like you could. Oh, there's a question.
Ah, there is.
Please.
Sorry, I didn't see it.
Thank you very much for your talk. I'm sorry, I don't know very much about this. My question first is, what kind of material you did these studies on? Because my question, my principal question is, where do you think the chloride comes from?
Sure.
In these experiments you did, and what material your experiments were done on?
Thank you. So the base material was so-called pure iron. But you being metallurgist, you know there's no such thing as pure iron, but it was very pure iron. I think it was 99.95 or something. Iron. So that's our substrate. So no chlorides, if that small impurity is nothing to do with chlorides. There may be some copper or God knows what, I don't even know what the impurity was in the original metal. Iron. I don't know the microstructure exactly, but it actually doesn't matter in this story. So, where do the chlorides come from? From the environment. So our solutions, the water solutions, were either having sulfates inside, or in this case that I focused on, chlorides inside. So we had sodium chloride in the solution. So when iron started corroding, it actually did that by having that chloride from the solution absorb on the iron and kind of helping the iron get out. Of course, the question is how, and this whole story is supposed to also guess how. There's 4 different ways that that can happen. By the way, the same is true without chlorides. If you just put water in there, no chlorides, then hydroxide, OH minus, not Cl minus, absorb on the surface and form compounds and help iron dissolve. So in a way, iron, which is a very reactive metal, it will always corrode, it will always dissolve, needs help. It doesn't just leave the iron lattice and go into solution. It needs help from chlorides or hydroxide or both in order to do that. So these environments, aqueous environments that have chlorides or hydroxides or both, are not good for corrosion of iron. Iron will dissolve faster than without them. Of course, it will dissolve even without chlorides and without hydroxide, but not as fast. It will take much longer, so these two are bad guys. The bad news is they're always there. You always have neutral water, there's always hydroxides, you almost always have chlorides. It's hard to have a natural environment with no chlorides. Even the water that comes from the ground has chlorides. Sometimes it has 25% chloride. Sometimes an enormous amount. So chlorides are such an important ion to study because it's always there. I hope that answers your question.
Hello. Okay, can you hear me?
Yes.
Well, thank you for your talk, and it's very, very interesting. I don't know anything about this, but I can see some questions emerging from my mind. How do you know there is no more paths for the dissolution? Because from what I understood, you can identify there are various paths because there are various loops in different frequencies.
Correct.
If there were 2 paths that share a common frequency or a common time scale, you could mix them.
Of course.
So is there a form to change the potential and the voltage and in other experiment identify them?
Yes, that's a very good question. It almost sounds like you've worked in this area. That is the biggest challenge. What if, like you said, if you have 2 pathways that involve, say, 2 different species, which happen at the same rate, more or less at the same rate. In other words, they will show up in these diagrams with the same loop, and there will be actually 2 of them on top of each other, but we can measure only the sum of the 2. So that is a problem, and there is no simple way to distinguish that. If you're a good scientist, you always have to worry about it like you do. So how do you distinguish it? Let's assume that one of those 2 compounds is a hydroxide and another one is a sulfate. It doesn't matter. But they happen at the same area, so when you do that EIS, always the same. So you don't even know there's 2. But then if you do it at different pHs, but at the same sulfate concentration, they will separate from each other. Or if you do it at the same pH, but different sulfate concentrations, they will separate each other. Or chloride, it doesn't matter, I just used an example of 2 pathways. So if they have a different composition, you can possibly distinguish them by changing the environment in which they are. Of course, you can change the potential, like you said, and that may also distinguish them, etc., etc. So that's the only way to know if there's more than 2 if they happen at the same time. And some of them show up at some high potentials where they don't show up at low potential. In other words, some of these pathways are there, but kind of dormant until you hit a particular potential and suddenly you say, oh, this is good for me now, so now I'm showing up. Like that chloride pathway shows up at the higher potential, the lower potential is kind of not there. It's there, but not doing much. There could be more. Still, having told what I just told you, there could be another pathway that we kind of missed because we didn't do enough combinations of parameters and we did not try to distinguish all the possibilities. But yes, there could be another 3 pathways which are not important maybe in this set of conditions, but if you do your experiments at pH 9 and we never went over pH 6, you can say, look, there's this stuff, you never saw that, it must have been there, and you're probably right. We just didn't play an important role at that condition we looked at. Yeah. Thanks, very good question. Yes, please. You need a microphone, I think, from someone.
Thanks for your talk. I have a question. Have you studied the effect of the reactivity of the iron in different phases or compounds related to the chlorides or the intermediate steps?
You have to repeat the question. I lost the first part.
Yes. Have you ever studied the effect of the reactivity of iron in different phases of or compounds related to the chlorides or the intermediate steps?
Well, iron, I think the short answer is no. But not because it doesn't exist, but we never saw it. I understand your question correctly. For example, iron could be in different microstructures. We never looked at that. We never looked at different microstructures of iron and see does after this microstructure respond to. We don't know there whether it's reactivity with I have no idea. Second question, I can probably write 5 different types of chloride compounds that are possible. And I have no idea which one of these it is. Because we haven't done experiments a bit like what he asked to distinguish them. Say if I write 5 different combinations, one may be perchlorate, another may be chloride this way and then chloride that way. I have no idea which, maybe they're all there, but I have no idea which one of them is more reactive and is more important. Why? Because we did not try to do experiments to separate. So in this presentation and in the papers, we said, you know what, we are going to write this chloride. But we're not really sure, but I want to write it that way so that when you read it, you have some idea what I think. Some of these older guys, this Kenan guy, he was very clever. He says, I'm not going to even write what it could be. I'm just going to say it is a chloride-containing compound, and I'm going to put a star, and that's what the star means. And I'm not going to speculate what it is, because I don't know. Well, that's very cool for me, but when you read the paper first time, you don't know what it's talking about. It looks like a foreign language. You need to read it 5 times before you figure out that that's what he did, and he doesn't want to say what things are because he doesn't know. So when you try to make these reactions, stick in your head. Because of this language he uses, which is very precise and very complex. So we went bravely and said, it is this chloride and that hydroxide, and here it is. You can say, I disagree, because it's something else, and it's good. It'll change when long story short, no, we have no idea which of iron-containing compounds are more reactive than others. We don't even know what all the possibilities are. They're our best guesses based on the experiment and the past image.
Thank you. We have a question
I'm supposed to make the microphone.
from the chat in YouTube. So, with these new insights, how much the localized corrosion initiation question advanced to be answered?
Then again, how much what?
With these new insights, how much the localized corrosion initiation question advanced to be answered?
That's a great question. The short answer is I have no idea. But let me try to show you one graph still. You know, being a scientist, I always try to speculate, see if I can find a graph. Okay, this one here. I didn't talk about this one in the talk, but it's easy to explain. These are all observations from the top. So imagine that, you know, I showed you those boxes which are like 3D. Imagine if you always look from the top and you kind of see all of the layers and they all are transparent, so you kind of see all the layers at once, at all the different depths. That's what these graphs are. Now, this is at different times, 3 minutes, 10 minutes, 1 hour. And this is for different compounds. There's chloride, this is oxide, hydroxide, chloride, some other chloride compound, pure iron, and then the same here. This is in a chloride solution, and this is in a non-chloride solution, sulfate solution. So, what's that going to do with the question? Like, here it is. You see here that in this solution here, you seem to have a lot more chlorides, which is logical because in this solution here you have this is a CO2 solution versus a non-CO2 solution. So it seems that chlorides, when they absorb, they create some kind of an environment where when they cover the surface, there are certain parts of the surface that they don't cover, and those are covered by an oxide or a hydroxide, etc. So you have a differentiation of where the chlorides are and where they're not. They're never completely occupying the surface. Whereas in non-CO2 solutions, you have a more uniform coverage. So the direct answer to this guy, I would speculate that chlorides always lead to a non-uniform absorption of other species, which eventually may lead to localized corrosion at these locations. Now, these are very small, these are nanometers, which may later on grow to become larger. So, there's something about the non-uniform absorption in the presence of chlorides, in this case CO2, which may lead to localized corrosion. But do we have a better understanding from this study? No. But if you go to Professor Marcus, the original guy's group, they looked a lot at stainless steels and passive materials, and some of the same issues, including chlorides, and there may be some good answers there, but not directly from these studies, but they will show some graphs like this, where there be like black holes, and that may be where pitting is originating, or initiating. The speculation. You?
For more questions, we have still some minutes.
Yeah? Yes. One at the back, middle.
Yes, thank you. You made a point to say that there's industry involved in all your projects.
Yep.
My question goes to, now that you have this information, how the industry is going to be interested in applying it?
Exactly.
Very much.
Very difficult. So that's where we scientists have to become salesmen as well. So you have to be able to sell this story to a person in Pemex who doesn't care at all about these details. But his pipeline pitted, and it was related to chlorides. They know, because they had an increase in chloride concentration coming from that particular well, and they had pitting and they failed some lines. But then you have to be a salesman and try to explain to him or her that, you know what, this is going to help us, because this is not the whole story, of course it's part of the story, but there's a beginning, and if I put it together with that and package it, we can help you, and maybe we can even suggest what you need to do to sort of reduce the probability of this happening. That's how we try. That's I guess the skill that you have to have in addition to just doing good science. If you want to get funding by the industry. Now, it doesn't happen randomly. We have been working with the industry for 30 years, and we've kind of been building that relationship. You have to kind of almost develop people in the industry who understand the big picture, who follow that, who come to your meetings, who understand that this is just part of the overall story, and they will support it over the years. That's how we do it. And it's not easy. Sometimes it fails. Sometimes companies just say, well, this is useless, we just leave. There's nothing there. They went in a different direction. So one of the key things we do is listen carefully. So when we have these meetings and I present this story and you're from Pemex, and if I see you reading your email all the time, I know there's a problem. I know that I'm going to lose you. And if it happens 3 times in a row at the meetings, we have a problem. I have to see what is your interest, why are you not interested, and try to get you engaged. And that goes for 20 people in the room. When we have these meetings. We meet every 6 months with all our industrial sponsors. All the students get up and talk, and I don't talk anymore, thank goodness, but they do. But what I do and my team, we watch, we listen. We listen to their questions, we listen to who's engaged, who's not, and try to respond and adapt. I hope that answers the question. It's tough.
Yes, thank you, and thank you for your lecture.
You're welcome.
Hi, it's a pleasure to meet you. How do you fit in or adjust your ACE result? It's a crazy. How do you have a result?
That's a good point. So that's a very good point. So if you go back to, EIS and say that you have, okay, let's pick this model. This is the complete model with 4 pathways. 4 different ways. Each of these is a reaction. 1 reaction, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 reactions. Each of them has a constant, kinetic constant. So it's like 11 constants that you don't know. And you have to fit them to make sure that whatever curls and results you got, that they match. So of course with the 11 constants, actually it's more than 11. I just did a quick count. There's forward and backwards. So there's like 22. And then plus some stuff that you don't know. So there's like 20 plus constants. That sounds like a mathematically impossible problem. And it kind of is. So you have to make some. I had 1 student try to do that. This work for me was done by 2 students. 1 person who was focused on the qualitative analysis. So I only showed you the curls and counted. I did not get into the detail. The other guy was trying to get those constants. He couldn't. Adam, the original guy, said he did it. And he added 22 constants, and there's all numbers. And we could not figure out how he got them. We replicated his work. The experiments were correct, but we could not fit any model to get the 22 constants the way he had. Some were close, some were like 10 orders of magnitude different. 10 orders of magnitude different. So we decided that this is an unreasonable task to try to fit a model of that complexity to any of these results. So what he did, instead of 4 schemes, he brought it down to 2. So instead of 24 constants, he had 6 or 8, I forget. And then out of those 8, some were obvious that they had to be in some range. They couldn't be whatever number. So eventually he ended up having to fit 3 or 4 and somehow got it to work. But when you take a scheme like this with four different pathways and 11 reactions, and you bring it down to only 2, you lose some of the physics. You kind of cheat in a different way. So those 4 constants you determine are kind of not real, and they somehow include more than they should. There's no other mathematical. So and that's an extremely difficult task to try to do.
Thank you.
Could I make a question? Thank you for your talk, Dr. Nesic.
Okay.
In those Nyquist plots, we have very small values in impedance. I agree with you, but so we are working at the anodic branch. We are working with a very high content of chloride, sulfate, etc. But these values are really they're really small.
You're talking about the low frequency.
No, not the values in frequency, but in impedance.
Oh, okay.
In the real axis and then yes, those values are really small. I don't know. So the corrosion rate should be very high, and we are in the anodic branch, is right, but we are in the perpassivation point. So I would expect that this value should be higher, not 1 ohm centimeter, square centimeter.
You're 100% right. But look at this. These 2 curves were collected for these 2 potential dynamics.
Yes.
And at this potential.
Okay.
So look at, this is DC, this is direct current.
Yeah.
Look at the magnitude of the actual DC. It is 100 amps per meter square, 1,000 milliamps per centimeter square. So this is driving this reaction crazy. You are running this reaction at an unreasonably high rate because you polarize half a volt.
In the anodic branch.
Impedance is so small because it cannot resist this polarization.
And with this corrosion rate, isn't it expected to precipitate iron carbonate? because we have a very large quantity of very large concentration of iron.
Well, apparently not here, but I know if I show you, and the other reason is that pH is acidic, so it kind of is able to handle that. But if you went to pH 6, this would have gone all the way to acidity, or if you went even with pH 4, but you went another few hundred millivolts up.
Okay.
So we caught it here just before passivity. This is the pre-passivation region. It's trying to, you see how it's kind of slowly, it's not really increasing, but we caught it. We did not want to go that high. But yes, it could happen, you're correct.
And you are working with 1,600 RPM.
Right.
Isn't it too high also? Because with turbulent flow, we just need about 500.
First, this is our rotating disc. This is all laminar flow, I think. But maybe it's slightly turbulent at the edges of the electrode. I don't know. The point being is, flow shouldn't matter. I mean, this is an anodic reaction. Flow shouldn't matter except for what you said. It may prevent passivation. If we did this in stagnant conditions, it may have passivated here right away because you build up the concentrations of species and it forms some kind of a surface there. So another reason why we work pretty high is to avoid that. We did not want passivation. We wanted to understand actually not even what happens here, it's what happens down there, because this is where our cathodic reactions are. This is where corrosion is. The rest up here was more to kind of understand what happens above, but up here I really don't care. So that's why we kind of focus on the active dissolution region. That's why the last not have the precipitation.
Okay, thank you. I think, I'm afraid that we do not have more time for questions. So, thank you, Professor Nesic.
Pleasure.
And thank you, all of you.
Thank you for the good questions. Sure. Do I need time to pack, huh?